Hi, everybody. Thanks for joining me today. My name is Jody Scollard. I'm a business development manager with Chicago White Metal. Really appreciate your time. We're going to talk about die casting and some high-level concepts. We'll dig into some design suggestions and alloy types and a little bit of everything. So appreciate you staying with us, and we'll get going. So what is die casting? From a high level, die casting is taking ingots of metal, melting it down, forcing that metal at very high pressures and temperatures into a die that's specifically made for your component. The part solidifies while in the die and then gets kicked out. So at the very high level, that's what die casting is. Obviously, there's a lot more that goes into it, but that's what it is. And when we say die casting, we're basically referring to the high pressure die casting process. And we say that just because it differentiates between high pressure die casting and other types of castings that you may have heard of, sand casting, investment casting, other things that are a bit different processes for different types of parts. So high pressure die casting, the goal is to get as much of the part made inside the tool as possible and minimize secondary operations that might be needed. So when you look at other types of castings that are on the screen here, whether it's sand castings, which are a bit bigger, bulkier, very thick wall, require some extra processes. Investment casting, which is another type of casting that has metal that's gravity fed into the die, so it's not injected under high pressures. You can't quite get the level of geometry, the level of features that we can in a high pressure die cast part. So the below image here, that is a high pressure die casting. So fairly thin wall, very intricate features that can be cast, and minimizing the any secondary operations, whether it's machining or other things that need to be done. That's the goal of a high pressure die cast part. Compared to the other types of castings, the sand and investment and other types, high pressure die casting will always have the lowest part price, just because it's a very fast process. It's very automated. There's very little labor that goes into it. And so for thin wall applications and parts with geometries that would be difficult to create with some of the other cast types, high pressure die casting is the best way to go. Some of the materials that are used for high pressure die casting, typically there are three families of alloys that we use: aluminum, zinc, and magnesium. We're going to touch base on all those and talk about some pros and cons, and we'll look at that here shortly. So why die casting? So again, we'll talk about the alloys that are available. They all have a good range of physical and material properties. We'll show a table here in a second of some of those. Again, you're going to hear this over and over in this presentation, but try to get as much of the part, and we call net shape, in the die as possible when it's being cast. From an economic standpoint, as little as you can do to the cast part as it comes out of the tool, that will just make your project cost much better. Other things to consider when we're talking about die cast process, sometimes if you have a multi-part assembly, there are ways to convert that to a single die casting, obviously reducing part count, reducing assembly time. It's a very economical and cost reduction way of looking at your product if there's ways to remove some of those extra processes. Good thin wall capabilities, good cast surface finish. Sometimes die castings can be used exactly as it comes out of the tool with no surface finish at all added. Other times you require paint or shot blasting or a wide variety of coatings that we'll talk about here in a minute. Again, as I mentioned, compared to any of the other casting processes, the high pressure die cast process will be the most economical way of making your part. And we mentioned on here what the typical volume levels are. There are times when you can look at a project that has, say, 500 pieces a year and have a justification for going to die casting. Typically, we'll see volumes in the 2,000, 3,000, 4,000 pieces per year numbers and up is where die casting becomes much more economical when you factor in the tooling cost. But again, there are times when 500 pieces a year, you can justify it, and it's a great cost reduction for something else that you're doing. The alloy properties, I'm not going to talk a lot about this, but I'll leave, obviously, if you're watching this, you can pause it and look at any properties you need to. We'll also happy to send you information about this if you'd like to see it as a PDF or other file type. But it gives all the chemical and physical breakdown of all the alloys that we cast. The Zamac, which is zinc, magnesium AZ91D, and the aluminum 380. So they're all referenced on here. We have nylon 6 as a comparison. So just to show you what, when you're looking at a plastic material, how the alloys for die casting compare. And the second page is just the other breakdown of that. So again, we're happy to give you any technical information that you need. We have some contact information at the end of the presentation that you can reach out. We'll get you whatever you need. From a tooling standpoint, there are a number of options available. This really depends on the type of product that you have, size, annual volume, complexity. So we take a look at all that and work with the customers to determine, okay, what's the best solution? Is it a 5,000 piece per year project and a single cavity is sufficient? Is it a 100,000 per year product and 4 cavities are a better option? Obviously, the more cavities you have, more economical the price is. So there are just know that there are a bunch of different options we can look at. What's on the screen here is a 2-cavity tool. You can see it's got mechanical side actions to form a feature on the top here. So those go up in this direction as the tool closes and forms the features from that side action. So again, there are multiple options, single cavity, multi-cavity. We can potentially do 2 different parts in the same tool, which is called a family tool. Again, economical option. Typically, when we're doing that, the parts need to be very similar in geometry and weights, so that when you're feeding material from one side to the other, that you're pretty close in the type of part that you're filling at the same time. So from an economic standpoint, what are all the factors that go into the pricing for a die casting? Some of these are fairly self-apparent, others may not be. Setup costs, obviously the raw material costs, we'll look at that here in a second. What's it take to actually process the die casting, your labor rates, machine rates, how fast are you cycling the part? High pressure die castings cycle very fast, especially compared to the other types of casting processes. Typically, we're in the 20, 30, 40-second cycle times per part. That's a typical thing for a die casting. Number of cavities that are in the product or in the tooling, that has an impact. Where we can automate, if it's something that we can use a cobot or a robot to do some operations instead of having a person doing it, that's a great opportunity that we always look at. Administration costs obviously go into it. And then a bigger factor that a lot of times people don't consider as being a big impact into the part pricing is what happens after the part gets cast. And I've mentioned a few times, and I'll continue to, as much as we can minimize what happens to the part after it leaves the die cast tool, that obviously makes your product much more economical. So any type of vibratory finishing, shot blasting, sometimes there's products that have the parting line needs to be polished away. If there's a leak specification for the product, sometimes we impregnate it with a resin to aid in leak testing. Other types of surface treatments, again, paint, powder coating, Cerakoting. There are dozens of different options. And then some other operations that we do internally for customers if needed. We'll leak test parts. We'll do some assembly for customers if there are multiple mechanical components that can be assembled onto a die casting. We can look at doing that for customers, or some special packaging and kitting, that type of thing. That's also options to look at for for after the part is cast, and it can aid in the economics of the overall project. Material costs. This is just a snapshot of where material costs are for the various alloys. Aluminum A380 is in the $1.35 per pound range. AZ91D magnesium is about $2.65, and zinc is around $1.65. So what this other portion of the graph does, it takes those metals and prices and normalizes it down to a cost per cubic inch range. So it tries to show that, okay, yes, magnesium is very expensive compared to the other alloys, but it's also very, very lightweight and low density. So when you normalize that to a cost per cubic inch, you can see it comes in pretty close to aluminum, which is a good thing. Zinc is on the other scale of that, very, very heavy compared to aluminum and magnesium. So when you normalize that down, again, it gets closer to the other two alloys, but can be a little more of an expensive product depending on how big the part is. But that's what this graph is trying to do. And then we look at a total project cost analysis, and this is looking at, okay, if we have a typical tooling package, let's say, this is just an example, say $75,000. That number will obviously vary depending on the part size and many, many different factors. But a typical die-cast tooling price package is between, say, $35,000 and $100,000. That everything usually falls within that. So if you look at this example and we're saying, okay, $75,000, let's look at how much per part that ends up being when you factor in the life of the tool. So for an aluminum tool, we typically say that it is good for 100,000 shots before some significant replacement or refurbishment is needed. So when you factor that in over $75,000, it's an easy calculation, but it's a 75 cent per piece impact to amortize the tooling cost over. Magnesium is very, very easy on tool steel, will last much, much longer than an aluminum part will. And we usually say somewhere in the $300,000 to $400,000, 300 to 400,000 shots for a magnesium tool before it needs some replacement. So when you normalize that over $75,000, you're in about an 18.5 cent per part range for that tool over the life of the product. Zinc is even easier on tool steel than the other two, and we usually say that's a million shots on a zinc tool before needing some refurbishment. So again, an even better cost payback when looking at zinc. So now let's look at some design strategies. So we work with our customers every day to try to help them get their product into the most optimum range for a high pressure die casting. And this is a very interactive process. We go back and forth and we try to understand what the customer needs, what the application is, how we can help design a die casting that really gets the most bang for your buck when going through this process. So we're going to look at some examples. We talk a lot about uniform wall thickness. We show some examples of that and why that's important. Fillets, radii, ribs, all good things that we try to look at when helping a customer design for die casting. Many of these are to aid in metal flow when the metal enters the cavity of a tool. That's a big thing we look at and try to assist the customer with getting their product in that type of condition. Minimizing machining stock. If there's some features that require machining after casting, obviously the less we can machine, the better from a cost standpoint. Typically, we try to maintain machining stock in the 15 to 20 thousandths of an inch range. And in the next slide, I'm going to show you kind of why that is, but that's a typical machining stock. We'll take a look at where the parting line is and other finishing considerations when looking at design. Draft angles, we talked about being able to combine parts as an opportunity. And again, add functionality where possible. Take advantage of the die casting process when looking at your part. So this slide right here is an interesting one. It goes back to my comment about uniform wall thicknesses and why that's important. So this is a cross section example. Basically, it's not a real part, but you can see that it's got a fairly uniform thickness down through here around both sides. It has a fairly uniform thickness when you're talking about the amount of material in between the walls here. And then it gets into a section that is much thicker. So you have a section that ends up being a pretty thick section. And what happens is when the very hot molten metal enters a die cast tool, the skin or outside of the part solidifies very, very quickly, say within milliseconds. And that is where your very good high integrity low porosity areas are in the skin of the die casting, say the first 20-25 thousandths of an inch. When you have these thicker sections, they take longer to cool. So that's going to be the last area of the part to solidify and cool off. And what happens is when you have a part that is going from a liquid state to a solid state, you end up having some kind of tearing and stretching inside the material, and that leads to shrinkage porosity. So that's what those little voids are in here, showing some potential shrinkage porosity. So this is one reason why, if you can have some very common wall thickness throughout the part, you minimize the amount of this type of area that has a cooling factor or timing different than another area of the part. This also shows why on the previous screen I mentioned how much of a machining stock to take into account. If we have to machine, for example, an area of the part in here, or maybe down inside this area here, we don't want to machine off all of the skin area, which is the really nice homogeneous area. So if we can minimize the machining to just take off a fraction of that, then you're left with an exposed surface that is very low porosity and still a good, a nice surface for you. So let's talk about some of the alloys available. Magnesium. Again, the alloy that we use is AZ91D. There are a few others out there, but this is the most widely used. Very, very lightweight. So when you think of magnesium, think of basically the weight of a plastic part, but much, much higher strength. So that's why a lot of times customers will come to us with an application, might have started out life as a plastic part, through some testing or in service for a while. They realize, okay, this part needs to be stronger, but we really like the weight of plastic. So that's why magnesium is a great option for that. Very easy to cast, easy to machine. You can get thinner walls with magnesium than you can with aluminum, so that's a plus. And as I mentioned previously, a long tool life. Again, 300,000, 400,000, 500,000 shots on a magnesium tool is not uncommon. So a great alloy for a high volume application to keep the tooling for a long time. Aluminum, that's sort of the go-to. So when people think of high pressure die casting, they'll usually kind of target aluminum as a first look at something. Many different types of aluminum alloys out there for die casting, very, very commonly used. People typically will just look at aluminum unless there's a need to look at either magnesium or zinc, and we'll talk about zinc in a minute. But very, very good material properties, easy to cast, and again, it's used very widely. So there's a very good established network of alloyers and finishing on aluminum die casting. So it's a good starting point for your project. On the other spectrum of weight is zinc from magnesium. So if you see magnesium as being the most lightweight alloy available, zinc is on the other scale. So very, very heavy in comparison. Typically used on smaller castings. Obviously, a lot of applications don't want that amount of weight in their product. So small castings, that weight impact is less. But zinc is used on many small type of applications, from cabinet locks and door locks and certain types of industrial fasteners are zinc die casting. So really suited much more for the smaller part. But again, there are applications that require the weight. There's if you have something that's going to sit on your desk and you have you need the extra weight for that to sit stable and not move around, then zinc die casting may be perfectly good for that, even though it's going to be heavy because you need it. You can typically get tighter tolerances held with zinc alloys. Very good impact strength. Again, die life is even better than magnesium for zinc. A million shots or more is not uncommon for a zinc tool. And can be cast with some amount of thinner walls, less draft. So a little more design flexibility with zinc than we have with aluminum or magnesium. So very good alloy. Unfortunately, a lot of applications, as I mentioned, just the weight is not, the extra weight is not an advantage there. But if you can, zinc is a great alloy to look at. So we'll talk about some part optimization techniques and strategies. Again, I would just suggest, contact us. We'll be happy to take a look at your product. This is the type of analysis we'll go through where we start looking at the initial design you're going to send. We're going to give you some feedback on, okay, there's maybe some thin wall conditions, thick wall conditions, add some draft, add some radii, just kind of the general things we take a look at when we see an initial model. But all these things, we look at it from a die caster standpoint to, how is that going to aid our process? But we also look at it on your side. How does this potentially aid your product from a cost standpoint? What can we do to try to minimize cost and make it a more competitive option for you? So just some examples, things on the screen of what we typically look at and how a part starts from some sharp edges over to rounded features, some thin steel conditions that we look at that you might not think about, but a lot of common things we look at from a part DFM analysis. Again, continue with that. Just an example here of a part that was started out as a CNC hog out of 6061 billet. We worked with the customer to add ribs and reduce material and really fine-tune the design for the high-pressure die casting process. Ended up being a tremendous cost save and still maintain the structural stability and properties that the customer needed for the application. But again, just an example of that. But we go through this type of DFM with every new part that we get, and it's a great collaboration with our customers. A little more on that line. This was a part that we started looking at with a customer. Initially, there was a number of different machining operations required. When we started talking to the customer about what exactly is needed in your product, how do the mating parts work? Let's see if we can get rid of some features or add some features to make your life easier. So we ended up adding this little tab at the corner here that took the place of another part. So we combined parts, helped in their assembly process. We also got rid of one of these bosses that's in here that's no longer there. That needed machining to start with and no longer needed machining. So overall, a more efficient part for the customer for their application, less costly, and very, very successful. As I've also mentioned a few times before, one of the opportunities for some really good cost reduction is taking multiple parts and converting to a single die casting. So if you see this image here, that started out as a couple of different die cast parts with a bunch of different fasteners and assembly operations, and through some pretty lengthy discussions with the customer and what could be done, what couldn't be done, we ended up coming up with a single die casting that took the place of everything above. So obviously, part count reduction, assembly reduction, less SKUs to keep track of in your inventory. This ended up being a tremendous cost save and a very successful product. This was magnesium, so a big magnesium part for sure, but it was a big success with our customer. This is another part that the customer came to us. It was pretty new. It was a replacement for something else that was in their assembly. They really asked us to take a look at this from a ground up standpoint, showed us, where all the features needed to be assembled, what all connected to it, and see what we could do to come up with a die-cast version of this part for them. And this is a bit of the story of how the iterations went. You can see our first effort at coming up with some ribbing to try to remove as much material as possible, but still maintain the functionality. It was good. Had some issues with some thin steel. Tool steel conditions would make it difficult for the tooling to form those features and not break and have issues long term. Second iteration, or actually third iteration, we developed more of a honeycomb type thing with the ribbing and internal structure. That was also good, but it'd be hard for metal to fill all those little areas and be successful. So it came out with the fourth iteration, which is pretty close to what ended up happening. A little more thicker ribs through the middle to aid in the structural needs that the customer had, but also would be easier to fill from a die casting standpoint. Also good steel condition. So a very good iteration that led to the end there. So once the design iterations are completed and everybody is happy with what the resulting design looks, we go through a very detailed flow simulation process where we'll simulate how metal is going to fill the cavity, fill the part, and see how the air gets from one side to the other. So you can see how the metal is flowing through this part, through the different ribbing and other features, and then out into the overflows on the opposite side. Some of the things that the software shows us is air pressure. So it's an indicator of how much pressure is inside the part, and we can identify any areas of concern or any areas that we feel like we should go back to the design and see if we can adjust to make it better. Also, it shows us some hot spots. So you can see there were a few areas in here where it would be hotter than others from a cooling standpoint when the part solidifies. This actually on the scale that we're showing here, these are actually fairly low, but they show as red just because it's on the scale. But it's a good indicator of where there might be some potential issues with porosity or non-fills or some other potential issues during the casting process. But in the end, this one was a very successful product, and the flow simulation showed that. So just as a final on this case study, a very successful collaboration with the customer, getting to know what their needs were, what their application is, where the design limitations are, was a huge factor in making this as successful as possible. So the last case study we're going to take a look at is an example of where we were able to reduce part complexity. So the part you're looking at on the screen started out as a sand casting, fairly large, a large part, pretty complex shape, had some very, very thick features. The customer came to us and was looking for a cost reduction and wanted to see if converting to a high pressure die casting would be an option. So when we start looking at the iteration that we went through from a design standpoint, we essentially had to take a step back. This is how the part started. We were having trouble trying to identify, okay, how could you make this part as a die casting? So we started actually stripping it away and went back and kind of looked at, okay, where are the mating points with the customer's assembly? What all are the main features that have to still be there? So we took it back to kind of its original form of, here are the touch points, here are the areas that mate to other surfaces. Let's build a die casting around that. So you can see the iteration as we transferred into a little more of a structure, and another iteration here at the end where we honing in on what the die casting is going to end up looking like, and something that could be castable. And then when you look at what happened toward the end, originally we would have had to do a very large side action to create all this internal geometry here, and that would be very difficult. So when we stripped it all down and we took a look at what actually needed to be in the product, where the mating surfaces were, we were able to come up with another design where most of this part can be made as an open and closed tool, and then have two smaller side actions to just create these surfaces at the bottom. So this is what mounted to their assembly, and those could be created with two small side actions in the tool, allow for much less complex tooling, faster cycle time, and resulted in really a really good sound die cast design for the product. So very, very successful. And then one of the last things we're going to talk about is print optimization. We really take a lot of time to look at this with our customers. We want to make sure that all of the features and notes and dimensions and everything that's on the drawing are only what's really needed. Sometimes we get drawings from customers and you basically can't read anything because there's just so many on there. And when you start looking at it, it's like, well, we don't really need all of these features. Some things can be controlled by the 3D model. We really just need what mounting surfaces, what really impacts the customer's assembly on these drawings, and same with the notes. So that's one of the things we'll take a look at with you, as well as the part design, is to look at the print and make sure everybody's happy with it. Something that can be maintained throughout the life of the product and easily inspected to, and that type of thing. So just another example of some of the collaborative efforts we go with our customer to look at when we're talking about a project. So print sometimes ends up being the last thing to look at, but it can have a big impact if there's some tolerances on there that just are too tight or tighter than need to be. That can have an impact on how the overall cost of the part ends up. So definitely consider that when you're looking at your drawing, and we're happy to look at that with you. So thank you again for the time. This was a great presentation and discussion. If there's any questions or comments or inquiries you have, if you have a part that you'd like us to take a look at with you, please use that email and phone number that's shown. We'll be happy to take a look and give you our honest assessment of how your part looks. Thanks again.